Ladies and gentlemen, welcome back. I hear you want to travel faster than light. Well, that's not going to be easy. In fact, we cannot even match the speed of light. But if you think about it for a second, isn't this unusual? I mean, if we push an object, it gets faster and faster. So why can't we keep pushing? Why can't we travel faster than light? A good place to begin would be the nature of light itself. Light is a combination of electric and magnetic fields, hence an electromagnetic wave. Though I will put a little asterisk here. Light actually has wave-particle duality, meaning it is both a wave and a particle. But let's not worry about that for now. So, it's an electromagnetic wave with the electric and magnetic components travelling together. You cannot have one without the other, and they travel at 90 degrees to each other, as you can see in this diagram. And if light has properties from both electricity and magnetism, how might those quantities be represented? Enter the electric constant and the magnetic constant. These physical constants represent how the electric and magnetic components act in a vacuum. And from these components, we can calculate the speed of light itself. Brace yourself for some maths. Let's start with the units for both of these quantities. These may look complicated, but it's quite simple. You have meters for length, kilograms for weight, seconds for time, and amps for current. You may have also noticed that these quantities share similar units. So let's multiply them together and see what happens. Cancels out, cancels out, cancels out, and cancels out. And add these two together, invert, square root, and voila, meters per second. The units of speed. And now, when we do the same to the values, we get the speed of light. Okay, so why does this matter? We've just found the speed of light in vacuo. But notice how the speed is because of the intrinsic nature of light itself. Provided you have a vacuum, light will travel at this speed. So if something isn't an electromagnetic wave, can it travel at the speed of light? Nope. But what if you were to try? What would happen? After all, in classical physics, if you push something, it will continue to pick up speed. But technically, this isn't actually what's happening. It's an approximation. Let's take our little rocket man here. Say he keeps travelling faster and faster until we get to 1/10 the speed of light. Here, things are mostly normal. So far, so good. It looks like we can do this. But when we start going half the speed of light, things get very strange. Our little rocket man starts gaining a lot of mass. You see, the extra energy had to go somewhere. And when we get close to the speed of light, the energy goes into your mass as well as your speed. In fact, at 90% the speed of light, our little rocket man is just over 3 times more massive than he was originally. And by 96% the speed of light, he is 5 times heavier than he was before. And at 99% the speed of light, he is a staggering 10 times heavier than he was before. You can see it happening on this graph. You can clearly see that as we go to higher and higher speeds, the mass increases even more sharply. This is special relativity. It's not just mass either. Your time is slowed, your length contracted. All of this can be thought of the universe twisting and turning, trying to prevent you from travelling faster than light. But if this is the case, If the universe works so hard to prevent you, a being with mass, from travelling this fast, why can light? Well, that's simple. Because light has no rest mass. Thanks for watching this video. I hope you all enjoyed it, and I will see you in part 2.